Kahoot. These are all related to electric current. There's 33 questions related to electric current. That's what we're doing. In order for there to be a flow of charge from one place to another, there must be yeah, both of the above, right? It's got to be a conducting wire connecting two places. You have to have a closed circuit, right? There also has to be potential difference. That's what a battery gives you, right? Like a AA battery might give you a potential difference of 1.5 volts. Right? Our battery got 12 volts. The cell phone chargers 5 volts, right? There's some impetus for the electricity to flow. Yeah, so you go. Combine that with the closed circuit. All right, points on the board. In solid conductors, electric current is the flow of yeah, electrons is the best answer. That's what's physically going on is that there are these flowing electrons. Why do metals make good conductors like for wires? Why do you make wire out of say like copper and aluminum, right? Because you guys learned in chemistry that metals, especially like in the middle of the periodic table, sometimes you see the phrase that sea of electrons, right? The electrons aren't really that steadfastly attached to individual atoms, right? So they can flow around, right? There you go. So they're conductive, right? Now, really, electric current is defined as the flow of positive charge, which is the opposite motion of the electrons, but it's a little technical detail. But yeah, there you go. That's the best answer. Electrons are flowing around, right? All right, got it. Sophia, Aaron, Blake, Kathy, Patrick. An ampere is unit of current. Current is measured in amperes. Guys, what is the unit for resistance? It's not amperes, it's what? Ohms. Yeah, resistance is measured in ohms. Current is measured in amperes. Potential difference is measured in volts. Power is measured in watts. Those are your main variables in units, right? All right. An example of a voltage source. Generator, rubber rod, per car battery, all the above. All the above. Right, nice. Yeah, right. I think that blue one, rubbing rods with fur, that was some of the first ways that people would charge things up. I'm talking about like 300 years ago, right? It was, oh, there's some kind of static electricity on it. I wonder what we could possibly do with this. Right? And then, yeah. So examples a little bit more sophisticated. Yeah. I got Blake, Aaron, Sophia, Patrick on fire. Electrical resistance in a wire depends on the wires. Ooh, this might be like tomorrow's lab. Tomorrow's lab. All right, so that's here's the answer right here. Right. So what's the resistance end to end? Well, the longer the wire, the more the resistance. The thicker the wire, the less the resistance. That's this relationship. And then there's also this material property, resistivity, which tomorrow you guys can figure out what is that for Plato, right? All right, but get there when we get there. Let's see. Did you guys get all the above? There you go. Okay, well, they went with conductivity rather than resistivity. Same idea, just a reciprocal. Yeah, all the above, all the above. Boom. All right, got Tucker, Blake, Sophia, Aaron, Patrick. Compared to thin wires, the resistance in thick wires is yeah, not as much, right? That was that inverse relationship I was just showing here. Let me flip back over, right? Point out exactly what answers that question, right? It's the relationship between these two variables here. right? The thicker the wire, that's a larger cross-sectional area, the less the resistance. There's an inverse relationship, right? Yeah, if you have a big thick wire, there's not as much resistance compared to a little thin wire. All right. Got Blake, Aaron, Sophia, Patrick. For most conductors, as their temperature increases, their resistance, take a guess. Yeah, okay, so that's the answer I'm looking for is resistance increases with temperature, and that's an approximately linear relationship. Let me kind of sketch out a quick graph for you guys. Okay, so if you look at what is, say, resistance in a wire as a function of temperature, probably like resistance in ohms as a function of temperature, maybe in Kelvin, something like that. Right. Okay, so let's say you start with like room temperature, then you make it colder and colder and colder. You can watch this resistance come down and down and down. Right? It really is about linear like that. Right? Now, when we get to quantum, quantum mechanics in May, I'm going to bring up this graph, and there's some of the specials that happens at a critical temperature, which depends on the material, is that the resistance can plunge all the way to 0 ohms in a wire. So that's possible too. Yeah. So that graph answers that question. Right. The higher the temperature, the less conductive the material, usually. Right. So most materials work like that. All right. There you go. Electrical resistance is measured in ohms. All right. Resistance in ohms. So energy is in joules, current is in amps, potential difference is in volts. Resistance is in ohms. We got Tucker, Blake, Aaron, Sophia, Patrick. If you experience an electric shock, where do those electrons actually come from? What's the best answer to that question? Somebody got it. Yeah, is actually from your own body. So you guys remember last week I had the Van de Graaff set up, right? Some students back there shocking themselves, maybe they make a shock chain, could shock each other, right? If you follow the individual electrons, they don't actually move that much. They might move like a fraction of a millimeter is all they move while you're getting shocked. What's really going on is that there's a potential difference across you, maybe like some number of volts in the Van de Graaff and then like 0 volts in the ground. There's a potential difference, and everything gets nudged a little bit, and each individual electron moves, maybe like a fraction of a millimeter, right? And that's what you experience as a shock, right? That's what I was saying earlier too. If I flip these lights off or on, you say, well, it looks like it happens immediately. So isn't that like a really fast movement of electrons? Well, not exactly. It's like if there's a whole chain of electrons in a wire, it's like everything gets pushed a little bit. Right. So yeah. So if you feel shocked, it's your own electrons being bumped a little bit. All right, Patrick, getting the points. The primary reason a bird can perch harmlessly on bare high voltage wire is like 10,000 volts. Why doesn't the bird get fried? Okay, yeah, that's the best answer I'm looking for. Said there's no potential difference across the bird's feet. So if the bird lands, let's say he's going down, land on a bare high voltage wire. Let's say it's like 10,000 volts. Right. So the bird puts down its right foot. Right. Okay, that's like touching the one end of an LED or a light bulb to like the positive terminal of a battery. Now he puts his left foot on the same wire. Well, that's like you take the other lead of your light bulb and put it on the same terminal of the battery, positive, positive. Well, that's never going to light the bulb. There's no difference, right? You need a potential difference. So the difference between 10,000 volts and 10,000 volts is 0, right? Now, guys, what would happen if the bird reaches down, touches his right foot on the 10,000 volt wire, and reaches his left foot and grabs a nearby tree branch? Now, is there a potential difference? Yeah. Now, does the bird get fried? Right. But there's got to be a difference. Right? If it's 10,000 volts and 10,000 volts, the difference is 0. Right. No difference, no current flow. All right, Blake, getting those points. Patrick's still in the lead. Alternating current. There you go. Yeah, alternating the direction of voltage of the power source. So say if you have a rotating magnet next to coils of wires, they're called inductors. There you go. Yeah. So that voltage will oscillate back and forth, alternating current. All right, Afe in the top five. Patrick's still in the lead. What's the frequency standard in these outlets here in North America? The frequency standard. Yeah, 60 hertz. Right. The potential difference standard is 120 volts. That's also true, but yeah, 60 hertz is the frequency. Yeah, so that'd be like, ooh, like 60 times per second, 60 cycles per second. A little bit faster than our brains could probably perceive, right? All right, we got Afe, Aaron, Sophia, Blake, Patrick. Current from a battery is always direct. Yeah, direct current, right? So the batteries in your laptops, the batteries in your smartphones, the batteries in the calculators, battery in your wristwatch, right? The cell phone chargers you're using last week and tomorrow, those are all direct current, right? Direct current. There's a direct flow of electrons that move really slowly in the wire. I think it's one of these questions coming up. But yeah, that's all direct current as opposed to alternating current. Here, this question: the net speed in electrons. Take a guess. How fast? Turn on a flashlight. How fast is electrons actually moving? Flip on the lights in this room. How fast are those electrons moving? My laptop running right now. How fast? Yeah, maybe like 0.01 centimeters per second. Right. Each individual electron moves really slowly. Right. But the energy is propagated quickly because it's like a whole like line of electrons, right? So there's a potential difference, and all the electrons get bumped just a little bit. It transmits energy all the way. Yeah. Right. No, that's for direct current. Right? If you're talking about alternating current, then there's no net movement. They just kind of slosh back and forth. All right. Where do electrons come from that produce heat and light in a light bulb? All right, nice. Yeah, that's the best answer. Is the bulb's own wire filament, right? Now, if you're talking about a flashlight hooked up to a battery, that's basically true, right? Now, if you run that flashlight for like an hour, yeah, eventually the electrons are cycling around. Maybe they like come from the wires and from the battery, right? That takes a while, right? But second by second, yeah, you're just looking at the electrons that are in the filament. Now, if you're talking about alternating current, right, where you have the say like a bulb inside a lamp, then that's an even better answer is only from the filament because now those electrons are just going back and forth, but they're only ever in the filament. Yeah, that's exactly it. All right. Uh, the number of electrons delivered to an average American home by an average power utility, say like over the course of a year, talking about alternating current. Yeah, zero electrons net. Remember, for alternating current, you just the electrons oscillate back and forth, back and forth, back and forth. There's no net movement of electrons for alternating current, right? And you can transmit energy, right? Transmit power, right? But no net movement of electrons. When we say an appliance uses electricity, what does that really mean? Does that mean electron kinetic energy is changed into heat and other forms of energy? Or does that mean the current disappears? There you go. Yeah, the first of those, right? Right. So that kinetic energy of electrons back and forth transferred into other forms of energy. Right? Right. The current does not disappear. The current in amps just keeps on through. All right. Got Aaron, Afi, Sophia, Blake, Patrick. If you plug in an electric toaster rated at 110 volts in a 220 volts outlet, the current in the toaster will be, sounds like Ohm's law, I equals V over R. we just double the voltage. Oops, what just happened to the current? If you double the voltage, the current is also twice as much. That's Ohm's law. I equals V over R. If you double the voltage, you're going to double the current. Okay. So here's another version of this question. If you buy a toaster in the United States, then that's designed for the American grid, right? And then let's say you take a plane trip over to England, where they have twice the voltage in their outlets. So if you try to plug it in there, now it's getting double the voltage what it's supposed to be getting, and probably not so good results. Right? Make it extra crispy toast. Got Tucker, Afe, Sophia, Blake, Patrick. Electric power is defined as, see, P equals IV. I think I should handle that one. You guys remember Joule's law? P equals IV. Is that power equals current times voltage? Power is current times voltage. Yeah, there you go. P equals IV. Power is current times voltage. Okay. The other takes on Joule's law, where you go voltage squared divided by resistance, or you could go current squared times resistance. I think those questions are going to show up later. All right. You know what? Let me do a quick pause right here. Let me switch back over to StotCam. Okay. Because I know there's a series of questions coming. It might be the next few questions, but pretty soon they're going to be based on Ohm's law. So remember, the current that flows is potential difference in voltage in volts divided by resistance. You can also rearrange this. Could you guys say V equals I times R? Could you also say R equals V divided by I? Right. So you guys ready to go on this one? Do some calculations coming up pretty soon. Right. And then after we're done with those, there's going to be the next few questions after those is going to be, well, any version of these. Power is current times voltage. Power is current squared times resistance. Power is voltage squared divided by resistance. You guys might remember from last week, completing all those Kirchhoff tables, that any one of these you do always leads you to the same power in watts. Right? Now, some version, or any one of those might be the most convenient to answer any particular question, depending on the scenario that you're given. All same power in watts. All right, let's see how we're doing here. Okay, it's not quite yet then. Compared to the thickness in a 60-watt bulb, the thickness in a 100-watt bulb, let's see, if it's more power for the same voltage, that would have to be less resistant. Less resistant. Here, I think you need a thicker wire. The thickness would be greater. Is that right? Would be greater thickness? Yeah, greater thickness. Right. Let me point out how I got that. Okay. So I was thinking, okay, we need 100 watts versus 60 watts, but maybe we're hooking them up to the same voltage source, the same like 120 volts. Right. So this is the same for both. Right. But different resistances then are going to result in different powers. Well, if we're looking at 100 watts versus 60 watts, we need more power. The way we get that is less resistance. And how do you get less resistance? You get that by having a greater cross-sectional area, which would correspond to a thicker wire. So if you look inside the light bulb, if you see a thick wire, that's less resistance, which therefore results in more power, like more numbers of watts. All right, so that's a whole chain of thought right there. All right, oh, Patrick, extending the lead. Power outlets in North America typically have a potential difference of 120 volts. Yeah, here in the States. Yeah, 120 volts. 120 volts. "12-volt battery connected to a resistor, 2 amps flows through in the resistor. What is the resistance?" Sounds like Ohm's law. Can you guys go V equals IR? So R equals V divided by I. Is that 12 volts divided by 2 amps? Guess what is 12 volts divided by 2 amps? There you go, Ohm's law. Okay, all right. Is everybody looking up on this poster in front of me that says Ohm's law? The next few questions are all related to Ohm's law. Let's see if you guys can navigate Ohm's law. All right, you guys got that one. The current through 10 ohms resistance in 100-volt power supply. I equals V over R. I equals V over R. What is 100 volts divided by 10 ohms? 10 amps. All right. 10 amps. Lots of points. What is the resistance of a toaster that uses 2 amps of current connected to a 120 volt power source? V equals IR, R equals V over I. V over I. What's 120 volts divided by 2 amp current? 60 ohms. Okay, yeah, let's step with the Ohm's law. Ohm's law. Just a rearrangement of that. When connected to 120 volts power supply, how much current is in a bulb with a resistance of 360 ohms? Sounds like I equals V over R. I equals V over R. Current is voltage divided by resistance. Is that voltage divided by that resistance? 120 volts divided by 360 ohms. It's a third of an amp. Right? I equals V over R. I, current in amps, is voltage divided by resistance. Yeah, that's a third of an amp. Okay, you guys good? All right. Voltage is 120 volts. Resistance is 110,000 ohms. I equals V over R. I equals V over Ohm's law. 120 volts divided by 110,000 ohms. Yeah, tiny decimal of an amp of current. All right. Current is voltage on resistance. Tucker, Afe, Sophia, Blake, Patrick. How much power? Oh, Joule's law time. How much power? 6-volt flashlight draws 1.5 amps of current. Can you guys go P equals IV? Power equals I, which is 1.5 amps times V, 6 volts. What's 1.5 amps times 6 volts? P equals IV. Yeah, 9 watts. 9 watts. You guys see Joule's law says P equals IV? I, current, 1.5 amps. V, voltage, 6 volts. Okay, you guys got 9 watts? That's Joule's law. Oh, Patrick got importance. Plugged into 120 volts wall outlet, how much current used by a light bulb rated at 200 watts? P equals IV. P divided by V equals I. Can you guys go P divided by V? What's 200 watts divided by 120 volts? It's like, yeah, it's really like 1.67 amps. So it's pretty close to that, right? Okay. Just take Joule's law, rearrange it a little bit. All right, so once you guys got that. 100-watt light bulb connected to 120 volt outlet. How much current flows? Ooh, P equals IV. P divided by V is I. What's 100 watts divided by 120 volts? .83 amps. So there's Joule's law all over again. P equals IV. You rearrange it, solve for current I. Measured in amps. All right. Light bulb plugged into 120 volts outlet has 0.4 amps current flowing in it. What's the power rating? P equals IV. Power is current times voltage. All right, so 48 watts I'm looking for. So you guys got power is current times voltage, P equals IV, current times voltage. So current is 0.4 amps, voltage 120 volts. Is that same thing as 4 times 12? What's 4 times 12? Oh, 48. And then the unit is watts, 48 watts. Okay. Double points. Electric heater is rated at 300 watts for use in a 110-volt circuit. The circuit breaker can handle 12 amps of current. How many heaters can safely operate? All right, so here, I'll walk you guys through this one if you beat me to the answer. All right, so I'm going to start with maybe P equals IV. But let's do it for a single electric heater. Let's say we're plugging one electric heater. Let's go P equals IV. 300 watts equals I times V. So I'm going to take 300 watts, divide by 110 volts. That tells me the current. I'm getting 2.7 amps for one heater. 2.7 amps. And we can go up to 12 amps. So what's 12 divided by 2.7? Looking at like 4.4. We can handle up to 4.4 heaters. Once you put on the fifth heater, it's going to overload the circuit. Yeah, so you can go up to 4, right? 4 and a little bit more, right? Once you put on the fifth heater, it overloads it. Okay. So a little bit of math there. All right. Oh, it's another double pointer. A heater uses 22 amps when connected to 110 volts. The electric power costs 10 cents per kilowatt hour. What's the cost of running the heater for 12 hours? Ooh. I'll solve it. You guys solve it. Let's see if we get the same thing. Here's a hint. Start with Joule's law. P equals IV. That's the first step. Ooh, all right. Hope you guys got that. Hope you guys got that. All right, so switch over here, solve this out. Okay. So here's exactly what they gave you. They told you the current in amps. They told you the potential difference in volts. They told you the cost of electricity, dollars per kilowatt hour. And they told you the time we're running this for, which is 12 hours. Okay. Now your first step is to figure out, well, what is the power in watts? So you know, power is current times voltage. That is Joule's law right there. Bam, Joule's law. Okay. Let's take this current 22 amps multiplied by this voltage 110 volts. 22 times 110, okay, which is 2420 watts. Right, so you guys got 2420 watts. Now, you guys know 1 watt is 1 joule per second. So I'm drawing 2,400 joules per second. Now we're going to do that for 12 hours. It's time for a dimensional analysis table. Dimensional analysis. Let's break it up with some railroad tracks. Railroad tracks. So we're starting at 12 hours. 12 hours. Right, so it's like our given values. I need to convert that to money in dollars. So all I know there's $0.10 per kilowatt hour. So hours goes away. So I'm doing kilowatts, right? Ooh. Here's my wattage, my power. I'm doing 2,420 watts, and every 1,000 watts is a kilowatt. So now the only unit left on the board is dollars, which tells us the cost. Let's do 12 times 0.1 times 2420 divided by 1,000, right? And that is $2.90 and 0.4%. So, well, about thereabouts, right? Or I think maybe you could round it up to the nearest cent. Maybe if they're going to charge you the next cent, like $2.91. Okay. All right, back over here. All right, a couple of you guys got that. It's a pretty tough question. All right. Oh, Tucker and Patrick. All right, for the win. Power line with a resistance of 2 ohms has 70 amps current in it. What's the power dissipated? Can you guys go P equals I squared times R? P equals I squared times R. All right, so I squared times R. I is 70 amps. Square that, square 70 amps times resistance is 2 ohms. Yeah, that gives you 9,800 watts. Ooh. All right, let's go to the podium. With the bronze, Sophia. With the silver, Blake. And the gold, oh, Patrick. Runners up, Faye and Tucker. Nice job, guys. Nice job. Oh, takes us about to the end of class right there. So, tomorrow, beginning of class, I will run a quick demo of that lab. Right. And you're going to figure out what is the resistivity of Play-Doh tomorrow. That's a wrap on today.